So this question isn't too difficult. It's just that we have to kind of take into account Newton's third law. So we're really just going to have to think about what each of these strings does. We've got three cards. They're sort of different sizes, and they're all being pulled forward by one string. And they tell us that there's they call this string 1, and there's a 6 Newton force on that. And then there's also these three other strings, and all of these are on wheels. We're ignoring friction in this problem. So the idea with this problem is this. When someone pulls a string over here, all of these cards are going to move together. So they're all going to move as one unit. So in a way, I could draw a free body diagram that looked like this, with adding up all of if this is 1 kilogram, this is 1.5 kilograms, and this is 0.5 kilograms. If I add all those masses up, I end up with a 3 kilogram mass total. And that's being pulled by a string of 6 newtons. We're ignoring friction, right? So then there's no backwards force. Well, this is just about the simplest type of problem you can do. It's F net equals ma. Ma equals the sum of the forces. So ma equals, in this case, the sum of the forces is 6. We know the mass is 3, so it becomes 3a equals 6. We can really simply find the acceleration of the whole system by combining all three of the masses into one. So this 6 Newton force is pulling all of it. And that's really how you find, and what we can say is each of these masses is accelerating at 2, because they're held together by this inflexible cord. So this is all 2 meters per second squared. And then we have to kind of think about each individual one. The question didn't even ask us for acceleration. The reason we're talking about acceleration is now we can use that to investigate each of these individual masses themselves. We want to know, the question is really asking us, what force must each of the short strings withstand? So really what they're saying is, what is the tension in this string, Ft, and what's the tension in this string, Ft? Okay, so let's call this Ft, this is string 3, so we'll call this Ft3, Ft2, and then this one was Ft1, I guess you could think of it that way. What I want to say is this: you can consider a free body diagram as any system of these three equations you want. If I want, I could draw a free body diagram of just the 1 kilogram mass. The key is, what are the forces that are external to this mass? Well, we can see that there is a force of tension pulling it forward, Ft3. That's the only force acting on this 1 kilogram mass. There's no friction pulling it back. We also know that's accelerating at 2 meters per second squared, right? So we have everything we need. Ma equals the sum of the forces. So that means 1 times 2 equals Ft3, which is the sum of the forces, and there's my answer. The tension in the third string is equal to 2 newtons. How about looking at the middle mass? So this is where it gets a little tricky. Let's look at the 1 kilogram mass, 1.5, kilogram mass. And let's look at all the forces acting on it. What are the forces acting on it? Well, we've got the tension pulling it forward, Ft2. Now, there is a 1 kilogram mass that it's pulling along. That's why it's exerting this tension force on the 1 kilogram mass. But Newton's third law says if this tension is the 1.5 pulling the 1, then there must also be a reaction force. And we are literally going to have to draw that on. And it's going to be exactly the same, Ft3, exactly the same magnitude. It's just opposite in direction. The point is, this 1 kilogram mass would feel differently if that 1.5 kilogram mass would feel differently if that 1 kilogram mass wasn't attached to it. So we cannot ignore this as one of the forces being applied. So then when we go to our MA equals the sum of the forces, we're going to have, so remember the mass is always, we're always analyzing a free body diagram. And in this case, the free body diagram we're analyzing is the 1.5 kilogram mass. When we looked at all the masses together, then we used 3 here, right? But now we're looking, and when we used 1 kilogram, we used the 1. But now we're looking at the 1.5. So I'm going to say this is 1.5 times the acceleration, which I already know is 2, is equal to, now thinking of sign convention, really it's ft2 minus ft3, right? We're subtracting those two. I know ft3, I just figured it out over here. It's only ft2 that I don't know. So we can rewrite this, ft2 equals 1.5 times 2 is simply 3 plus ft3. And that equals 3 plus 2. So ft2 is equal to 5 newtons. And that's the answer to this question. Now, again, just to emphasize the main concepts we're getting at here, the main thing here is that you cannot ignore the reaction force when you consider this. Okay, there is a third way to go about there's another way to go about finding the tension Ft2. I could have, this is an alternate, but equally valid and equally interesting. I could actually consider these two masses together. I could call this a system. I can do that. Over here, I called all of them a system that were 3 kilograms. Now, I could say, here's a system with a mass of 1.5 plus 1, so 2.5. What are the forces external to this system? Well, now you see that Ft3, the action-reaction there, is internal to the system, and we don't draw it on our free body diagram, because the forces we draw here are only external to the system. So the only force that's external to the system, this 2.5 kilogram mass, is Ft2. We still know it's accelerating at a meters per second. So when we go to do our MA equals the sum of the forces, we get 2.5 times 2 equals Ft2. Well, look what we get. That means Ft2 equals 5 newtons. Same answer we got over here. Two different methods, but they are both valid. And what I'm hoping they illustrate is this concept of system. A system is any mass or masses. Okay, anything can be considered a system, but when you draw a free body diagram, you only draw the forces external to that system. So when we drew the 1.5, we had to include the Ft3, but when we included that 1 kilogram in our system, that internal force was not drawn on our diagram, and this is all we had left.